Modern AI models are massive because each weight uses 32 bits. Shrinking these to 8 bits makes the model 4 times smaller, but fitting them onto mobile devices requires protecting the model's intelligence. This shrinkage happens through quantization, mapping continuous values into discrete buckets. While these integer slots save space, grouping points together destroys the subtle differences which previously defined our model's high accuracy. Usually, post-training quantization converts a finished model all at once. By forcing weights into buckets after training, rounding errors compound because the model never had the chance to adapt to lower precision. This failure occurs because rounding shifts weights from smooth landscapes to jagged, stepped ones. These small errors compound across every layer, but we can actually train models to survive these precision cliffs. Quantization-aware training solves this by injecting noise through fake quantization nodes. This ensures the network learns to maintain its predictive power while operating under hardware constraints during training. Inside these nodes, fake quantization simulates hardware limits by mapping weights to integers and back again. This intentional noise forces the network to become robust before the final precision is permanently stripped away. However, rounding creates a staircase function where the slope is 0, destroying gradients. Because these flat steps block the learning signal, weights cannot update. But what if we simply pretend these rounding cliffs don't exist? To bypass this blockage, we use the straight-through estimator. In the forward pass, rounding simulates quantization noise. But for the backward pass, we pretend rounding never actually happened. Gradients flow straight through, allowing the weights to update and learn effectively despite the discrete rounding steps. Consequently, quantization-aware training builds rounding errors directly into the learning loop. This helps the model adapt as it iterates, allowing weights to settle in safe zones where precision loss matters least. This awareness forces weights to migrate. While many start near dangerous rounding boundaries, training pushes them toward safe midpoints. By avoiding these precision cliffs, the model actively minimizes its final deployment error. QAT bridges the performance gap, recovering nearly all accuracy lost during standard quantization. This results in models 4 times smaller and significantly faster, with negligible trade-offs. Ultimately, quantization-aware training is the bridge between research and deployment. By shrinking models without losing intelligence, we can push AI onto everything from smartphones to tiny industrial sensors. The QAT story is one of proactive adaptation. Applying quantization after training results in accuracy drops because weights aren't prepared for rounding error. But by training with quantization noise from the start, the model adapts, maintaining performance when deployed to resource-limited devices. Don't just suffer the noise, learn to thrive within it.